Hey guys, in this video we are going to discuss Newton's method. So we know so far we have talked about two methods to find roots of a nonlinear function. So earlier we have discussed bisection method, how to use that bisection method to find roots. So we know that bisection method converges to the root linearly. And next we talked about fixed point iterative method. That one also converges to the root linearly, right? So now we are going to discuss Newton's method, right? So we already know the goal. What is the goal? The goal is, this is the goal. Goal is for a given a function f of x. So we want to find a root r such that f of r is equal to 0, right? So before doing this you have to check whether the function is continuous, and so you have to specify, you have to identify an interval AB, right? So make sure that you check these things. First you have to check the function is continuous on the interval, on the considered interval, and check whether the function at the endpoints, function values at the endpoints are opposite, right? So then we can say there exists at least a root in between a and b. Then after that we find the root, then we apply different methods. So you can use bisection, fixed point iterative method, or Newton's method. So today we are going to discuss Newton's method, right? So this is our goal, finding a root r such that f of r is equal to 0. So the main idea of the Newton's method is the following. So let's draw a graph. All right, so let's consider this is our function, x-axis. This is your function. Let's do it in a different color, right? Right, this is your function f, right? Here we have a root r, f of r is equal to 0 at this point. F hits x-axis at r, right? So given, so these are the approximates, these are the iteratives, right? So let's start off our method from here, xk, right? This is your approximation. So xk, so given xk, the next approximation xk plus 1 is determined by approximating f as a linear function at this point. So here we approximate function value, the function f as a linear one. So that means this is the tangent, this is the tangent line of f at xk, right? So we approximate the function value at this point is is linear. So we approximate the function is linear at this point. Now we can solve this one very easily. So we can find, so this is our next iterative. So next iterative is k. Let's denote it x sub k plus 1. This is our next iterative. So how do you find this next iterative? Just finding the intersection point of this this tangent line and the x-axis. So you can find that. So let's write a equation for that. So let's derive a formula, right? So this is the tangent point, this is the tangent line at xk. So the slope, of this one is, f prime of xk. So this, because this is the tangent line at xk point, right? So f prime of xk is equal to what? So how do you find this tangent? So these coordinates, right? This is f of, this coordinate is x coordinate is xk, y coordinate is f of xk, right? This coordinate, this is there is no y coordinate, x coordinate is this. The slope of this line is can be written in this way as well. The rise divided by run. Rise is f of xk minus rise, this height, this length, minus 0, this is the rise and this is the run. Run is xk minus xk plus 1. You can rearrange this equation. So let's solve this for x sub k plus 1. Let's do cross multiplication, right? So xk minus xk plus 1 is equal to is this one times f prime of xk equals f of xk, and let's assume f prime xk is not equal to 0. Otherwise you cannot find an intersection point, right? So if that is the case, this tangent line is parallel to x-axis, there is no intersection point, so you cannot choose a Newton's method. So make sure, you cannot use Newton's method at that case, for that case. All right, suppose f prime evaluated at xk is not equal to 0, then you can divide both sides by f prime of x k. Then I rearrange the equation. I solve that equation for x k plus 1, which is equal to xk minus f of xk minus f prime of xk. So this is the Newton's method, Newton's formula, right? K is equal to 1, 2, 3. This goes on, right? So before considering an example, let's verify the following results. So result number 1, result. Alright. Newton's method is a fixed point iteration. Newton's method is a fixed point iteration. Fixed point iteration. Alright, that means, so this iteration, this Newton's iteration is a fixed point iteration, right? So suppose this is your g of x. Let's pick the function g as this one, x minus f of x divided by f prime of x, and assume that f prime f prime is not equal to 0 over a neighborhood, on some interval, right? Let's assume f prime is not equal to 0, right? Then this is g of x sub k, that is g of x sub k, right? If you plug this number into the g of x, if you plug this number into here, you get the right hand side of Newton's formula, right? And the left hand side is this. Right? This looks like fixed point. So if this is a fixed point, we have to show g has a fixed point. G has a fixed point. Let's now we are going to show that the fixed point of g is a root of f. Let's show that. Here we assume that f prime evaluated at r is not equal to 0. Let's assume that f prime is not equal to 0 at r, right? Alright, so what we are going to show, that the fixed point of g is a root of f. So this is the fixed point. That's r is the fixed point of g. That means r is equal to g of r. since R is a fixed point. Suppose let's, yeah, if R is the fixed point of G, then this is true, right? Now we are going to show this fixed point is a root of f here, right? So let's plug this number into here. Plugging numbers, plugging the root r, plugging r into here. R minus f of r divided by f prime of r. Here you have r. You can cross this off, so you end up with minus f of r divided by f prime of r is equal to 0. This means f of r is equal to 0. That means f r is a root, r is a root of f. This means r is a root of f. Therefore, the fixed point of G is a root of f, right? The fixed point of G is a root of f, right? So you will now see that not only is Newton's method fixed point iteration, it is the optimal one or the best one. The Newton's method is the best one. So we prove that the Newton's method is a fixed point iteration. Now we are going to show the Newton's method is the best, the optimal one, optimal fixed point iteration, optimal one, the best one, right? So recalling the error analysis for fixed point iteration, so we know that the convergence of fixed point iteration depends on G prime. Do you remember? Wait a second. Here we go. So this is the convergence of fixed point iteration. So this is the current stage, this is the previous stage, right? The error at the current stage, this is the error at the previous stage. The error of the current stage is equal to modulus of G prime times the error of the previous error at the previous stage, right? So we know that the fixed point iterative method converges whenever this one is constant, this one is less than 1. So we know that fixed point iterative converges linearly if this value here less than 1, right? Bounded, this value is bounded by is less than 1, right? So if you have very small number here, the fixed point iterative method converges very fast, right? Converges fastly, right? So what happened, this bit is equal to 0. So that is the best case, that converges very fast, right? So for Newton's method, this one here is equal to 0. That's why I said the Newton's method is the best one, optimal one. The G prime at evaluated at R, evaluated at R is going to be 0. That's, yep. So let's note that. A fixed point duration x equals g of x is optimal if g prime of r is equal to 0, where r is the fixed point. Right, so let's check that for Newton's method. This is a function g we picked from Newton's method. So this is the function we picked for Newton's method. G of x would be, what is g of x? G of x x minus f of x divided by f prime of x. So this bit is not equal to 0. Let's take the derivative of this. 1 minus, so this is we had to use quotient rule to get the derivative. F prime x is square the bottom one, and write the bottom function and differentiate the top function. Then this becomes squared minus, and we write the top function and the derivative of the bottom function, f double prime of x. Assume this one is axis, the f double prime axis, right? So we can simplify this. Here you have here this one, so here this one goes with this, and then you have 1, this one cancels with here, and here you have f of x, f double prime of x divided by f prime of x squared. Alright, so let's evaluate g prime at r. So what happened? So we know the fixed point of g is a root of f, then this becomes 0, then everything becomes 0, right? Therefore g prime evaluated at r is equal to 0. Therefore Newton's method is the optimal, the best one. The Newton's method is the best fixed point duration method, right? All right, so hope you understood this one here. So in my next video I will do detailed convergence analysis for Newton's method. to see how fast Newton's iteration converges, right? So, all right, see you.